Welcome back. So this is the first part of lecture 5. In this lecture and the next few, we're going to talk about some sort of standard distributions that are seen a lot in applications, but we're still going to have links back to measure theory that we've been working on so far. Okay, so first off, to see the link between measure theory and what we're going to get to, so we've seen for the dice, say you have a 6-sided dice, 6-sided dice, and roll it n times. Well, there are different examples for what we've had as the sample space here. So one of them you could contain, well, omega 1 ... omega n, where omega I is in 1 up to 6. And this you could think of as representing exactly which rolls you had and the order they came in. Okay, but we could alternatively consider just this other set. So this k1 ... k6, where ki is in what Georgie calls z plus. So in other words, 0, 1, 2, ... and with the sum of these ki equals n. Okay, where here we can think of this set as modeling just, well, only recording how many ones we saw in the n rolls, how many 6s we saw in the n rolls, and everything in between. Now, these are both perfectly good probability spaces. In some sense, you could very easily guess what should be the probability space here, and to a slightly lesser extent, you could guess what it is here. But you can actually, by looking at a probability measure on this bigger set, we can use the method that we had from last lecture to construct the natural probability measure on here. Okay, so if we have a probability measure on omega, which we'll just equip with its power set, since these are finite sets, we don't have to worry too much. And we let x from omega to omega dash be the function which takes, well, omega 1 up to here, n to number of ones, ... number of 6s. Well, and suppose we're also equipping omega dash. We equip omega dash with its power set as a sigma algebra, and then this map x will be a perfectly good random variable, so we can use it to push forward p from omega to omega dash. Okay, so like then p of x is natural in some sense, probability measure on the power set of omega dash. Okay, so great. This is going to be a very standard procedure we're going to use for the next couple of lectures to go from sort of a sample space with a lot of information, which maybe we don't care about, have some sort of map from it to a smaller sample space, and then obtain a probability measure on the sample space. Okay, the first probability distribution that we're going to look at, we have actually already seen. I preempted a bit, but I'll just remind you what it is. So uniform distributions Okay, so if we have some finite set, then we can define the uniform distribution, U omega, which is defined on the full power set of omega to 0, 1. And well, it just counts what proportion of omega is contained in a set. So it takes A to the size of A divided by the size of omega. Okay, and this is sort of a fairly obvious one to put on this sample space because, well, if you assume that the dice is fair, then all of these, every possible outcome should have the same probability, and there are finitely many of them. Okay, so this is by definition the uniform distribution. Now, if omega isn't finite, maybe I'll say not less than infinity instead, then this obviously doesn't work. But as I mentioned previously, we do have the Lebesgue measure on R, and the Lebesgue measure is translation invariant, and that's sort of like uniform, okay? Because you can there's some large group of symmetries that the probability measure is invariant under. However, the Lebesgue measure, so Lebesgue measure on the real numbers, or D with Borel sigma algebra, D-dimensional Borel sigma algebra. So this is translation invariant, so it's sort of uniform, but the Lebesgue measure of RD is infinite. So you can't do this what we've had up here for the uniform distribution, but if you've got some Borel set with positive finite measure, then you can you can define the uniform distribution on on omega, and this is what you would sort of expect. It's compare the volume. So define the uniform distribution on omega to go from the restricted Borel sigma algebra to omega to 0, 1, and it just takes a set A and maps it to lambda of A divided by lambda of omega. Now, in this case, you could say, well, omega isn't translation invariant, so how is this uniform? But you can check very directly that if A and a translation of A are both contained in omega, then this uniform measure here will assign the same probability to both of them. Okay, so it's sort of restricted translation invariant. Okay, and we'll end the lecture here. So, well, not quite. These two here are going to be our sort of starting point to then apply a procedure like what we've described up here to obtain probability measures on more interesting spaces, or spaces which keep track of less information. All right, thanks.